Imagine walking into like a sterile, intensely air-conditioned conference room.
Oh, the classic tech interview setting.
Right. And an engineering director at one of the top tech companies in the world just slides a dry erase marker across this massive glass table. They look you dead in the eye and say, design a real-time chat platform for me, something exactly like WhatsApp or, Telegram or Slack.
It sounds almost aggressively simple on the surface, right? Because
Sure.
we use these applications constantly. We take the UX completely for granted.
Yeah, I type hello, I hit send, and it vibrates in your pocket like half a second later. It feels like magic. But then the interviewer in the scenario drops the actual constraints on you, the
And
numbers.
that's where the panic sets in.
Exactly. They tell you that your architecture needs to handle 2 billion registered users. It needs to support 500 million daily active users. You need to process 100 billion messages every single day. And the kicker, you have to guarantee that those messages are delivered in under 500 milliseconds, and the entire system has to maintain 99.99% uptime.
Which is the exact moment the illusion of a simple chat app just, well, shatters into a million pieces.
Yeah.
Because when you start dealing with the scale of 100 billion messages a day, the standard textbook rules of software engineering just evaporate. You can't just spin up a standard SQL database, throw a simple web server in front of it, and expect it to survive.
Right, it would just instantly melt.
Literally, at that volume, the basic physics of computing, I mean, the latency of fiber optic cables, the rotation speed of physical hard drives, the memory limits of a mobile browser, all of that becomes your immediate enemy.
And that is the exact specific lens we're adopting for today's deep dive. We are sitting in the interviewer's chair. We have this massive stack of architectural blueprints, system design notes, and engineering breakdowns, which are our sources for today. And we are evaluating this chat platform design exactly as an engineering manager would evaluate a senior candidate for a back-end architecture role.
Yeah, we aren't just listening for buzzwords here.
No, absolutely not. We're hunting for those critical, battle-tested, senior-level pal-outs that separate a genuinely globally scalable design from, a system that would just melt down in the first 5 minutes of deployment.
Right, we're looking for the candidate who fundamentally understands the mechanics beneath the tools. Someone who knows not just what database to use, but how that database actually writes bytes to a physical disk, and more importantly, what happens when that disk inevitably fails.
Because it will fail.
Oh, guaranteed.
Hmm.
At 2 billion users, failure is no longer a possibility. It's a statistical certainty happening every single second.
So we'll be tracking the journey of a single text message today. From the moment your thumb hits send, through the dual broker delivery pipeline, deep into the massive storage arrays, and into the absolute chaos of high concurrency group chats.
And finally, into the clever front-end illusions your phone plays on you to keep the backend from catching fire.
Yes. It's a fascinating map of trade-offs. It really reveals how much smoke and mirrors are required to make immensely complex infrastructure feel like instantaneous magic to the user. So let's start the journey. The message begins. I type a text to you and I hit send. That payload leaves my phone's cellular antenna and hits the company's backend server.
Okay, great.
Now, if I were a junior developer building a weekend project, my server would probably just look up your IP address, try to open a connection directly to your phone, and hand you the message.
The synchronous point-to-point approach.
Yeah.
The server holds the incoming connection from your phone open, frantically searches for the connection to my phone, and tries to pass the data along in one continuous motion.
But with 500 million daily active users, I'm assuming that approach hits a brick wall almost immediately.
A brick wall made of completely exhausted server resources. I mean, let's think about the physical reality of a server. Every active connection to a phone requires a certain amount of memory and a dedicated thread or process. What if my phone is off? What if I'm walking into a subway station and my cellular signal drops for 20 seconds?
The server's just stuck waiting.
Exactly. The server cannot just sit there, freezing up its memory and computing power, waiting for my phone to respond. If it does that for millions of messages simultaneously, the server just runs out of threads, stops accepting new connections, and crashes. It needs to offload that incoming message immediately and free up its resources.
So the server's first instinct has to be, I need to put this message down somewhere safe and get back to work.
Precisely.
Which brings us to the message broker pipeline. Now, looking at the architectural blueprints in our sources, a mid-level candidate might just draw a single box on the whiteboard labeled message queue and move on.
And they would fail.
Right, because the senior candidate introduces a highly specific dual broker system. They use two entirely different technologies running in parallel Kafka and Redis Pub sub, But why? Why do we need two different tools just to move a message from point A to point B?
It comes down to a fundamental conflict in distributed system design, which is the need for absolute durability versus the need for blistering speed. You have these two competing requirements. First, durability. If you send me a message and a server somewhere in an AWS data center suddenly loses a power supply a millisecond later, your message cannot be lost.
Right, it has to be written down permanently.
Exactly. It must be written down permanently, and that is the exact problem Apache Kafka was built to solve.
I want to break down Kafka, actually, because it gets thrown around a lot in system design. I sort of picture Kafka as this massive, heavily fortified industrial sorting facility. Like, it's incredibly organized. Every single message that arrives is stamped, ordered, logged, and written directly to a physical hard drive. It's an immutable log.
That's a great way to put it.
And it's replayable, right? Like,
Reliable.
if a delivery truck crashes down the line, Kafka can just look back at its physical logbook and send another copy.
That is an excellent way to visualize it.
Yeah.
Kafka's core strength is its sequential disk I/O, meaning it doesn't jump around the hard drive looking for places to put data. It just appends data to the end of a file as fast as the disk can physically spin. It is practically indestructible once it acknowledges receipt of a message.
Okay, but if Kafka is this bulletproof industrial sorting facility, why do we need anything else? Like, why not just have the servers reading from Kafka and pushing the messages out to the users?
Because your industrial sorting facility, while incredibly reliable, is just way too heavy for a real-time chat application's latency budget.
Ah, right, the 500 millisecond rule.
Exactly. Remember our constraints. We have a strict 500 millisecond window. We need that message to go from your device across the internet through the back-end processing and onto my screen in less than half a second. And Kafka writes to disk.
And disks are slow.
Right. Even with modern solid-state NVMe drives, disk operations take time. Acknowledged times take time. If we rely solely on Kafka's disk-based readers to push the message out to the active live connections, we are going to really struggle to hit that sub-500 millisecond guarantee consistently, particularly during massive traffic spikes like New Year's Eve or a major sporting event.
I see. So the fortified facility is perfect for making sure the package survives a fire, but we wouldn't use a massive armored freight truck to rush a single envelope to a house right down the street.
Exactly. You'd use something faster. And that is where the second half of this architecture comes into play, Redis Pub Sub.
Okay, let's talk about Redis.
Redis is a fundamentally different piece of technology. It operates almost entirely in memory, in RAM. In the Pub Sub context, it doesn't bother writing anything to a hard drive at all.
None of it.
None of it. It is designed for absolute blistering volatile speed. It handles what the architecture calls the last mile push.
So let's carry the analogy forward. If Kafka is the armored truck, Redis Pub Sub is like a hyper-fast bicycle courier waiting at the very edge of the network.
I like that.
Right. The instant the backend receives your message, it hands a copy to the byte courier. The courier sprints to the WebSocket gateway, which is the specific server holding the live, open connection to my phone, and just shoves the message down the pipe. And because it's operating in RAM, Redis offers, what, sub-millisecond publish times?
Precisely. But here is the critical vulnerability and why the dual system is mandatory. Redis Pub Sub is inherently ephemeral.
Meaning it forgets.
Right. If that hyperfast byte courier arrives at your door, meaning the WebSocket gateway, and you aren't home because your Wi-Fi just blipped out, the courier does not wait. The courier does not leave a sticky note on the door. The courier just tosses the package into the void and rides away. The message vanishes from Redis entirely.
Wait, if Redis just drops the message the moment I lose connection, how does the system not lose the message permanently? If I'm paying for my cellular data, I'm going to be furious if my conversations have holes in them just because I walked into an elevator.
And that is the genius of pairing them together. You don't use them sequentially, you use them in parallel.
Oh, at the same time.
Exactly. When the backend receives your message, it immediately writes it to Kafka to guarantee it is safely stored on disk. Simultaneously, it pushes a copy to Redis Pub Sub to attempt the lightning-fast delivery to the recipient's active device.
So it's literally a race.
A coordinated race, yes. If the Redis delivery succeeds, fantastic. The user receives the message in 50 milliseconds. The UI feels incredibly snappy. But if the user happens to be disconnected and Redis drops the message, the system doesn't panic. Kafka still has the durable copy safely on disk.
So when I get back online?
Right. When the user's phone reconnects to the network, say 3 seconds later, their app queries the backend. The backend checks the durable storage backed by Kafka, realizes there's an unread message, and delivers it. You achieve the sub-millisecond speed of memory with the absolute safety of a hard drive.
Wow. It's a highly pragmatic compromise. Now, I do want to mention something from the source notes. They pointed a modern alternative here, which is Redis streams. What is the distinction there?
Yeah, so Redis Streams is essentially an attempt by Redis to offer Kafka-like features. It provides durability and ordering per stream, unlike the purely volatile pub submodel. For a moderate-scale application, maybe a few million users, a senior engineer might actually suggest Redis Streams to simplify the infrastructure.
Because Kafka is a beast to run.
Oh, absolutely. Running a massive Kafka cluster requires dedicated DevOps teams. It is notoriously complex and expensive to maintain. If you can use Redis for both the fast push and the durable queue, you really reduce your operational overhead.
But not at WhatsApp scale.
No, absolutely not. When you cross into the realm of WhatsApp scale, 100 billion messages a day, Kafka's mature ecosystem, its highly specific partition model, and its raw, disk-based horizontal scaling capabilities make the mandatory choice for durability.
Okay, so the message has blasted through this parallel pipeline. It was logged safely in Kafka and zipped over to the receiver via Redis, but moving data at this breakneck speed across unreliable networks introduces a whole new category of terror for a software engineer.
Oh, network reliability.
Yeah, networks are fundamentally flaky. Like, what happens if my phone sends a message, but the network drops right before the server can send an acknowledgement back to my phone? My phone might think the message failed, so it automatically retries and sends the exact same message again.
Right.
Or what if the Kafka cluster stutters and accidentally processes the same message twice?
Well, you just described one of the most notoriously difficult problems in distributed computing. It's known as the at least once delivery problem.
At least once.
Yeah. In a system involving thousands of network hops, you can almost never guarantee that a message will be delivered exactly once. The mathematics of networking dictate that you can only guarantee it will be delivered at least once. And if you guarantee at least once, well, duplicates are a mathematical certainty.
Which is a terrible user experience. I mean, I don't want to see, where are you? Where are you? Pop up on my screen 3 times just because a router somewhere in Chicago had a momentary buffer overflow. So how does a senior architect handle deduplication at a scale of billions?
The architecture actually shifts the responsibility of uniqueness all the way to the edge of the network, right onto your physical phone.
Wait, my phone generates it?
Exactly. Every single time you type a message and hit send, your phone's operating system generates a client message. This is a UUID, a universally unique identifier. It is a long, complex string of characters that is statistically guaranteed to be completely unique across the entire planet for that specific message attempt.
So the message carries its own, unforgeable fingerprint from the very millisecond it is born.
Yes. Now let's track that fingerprint. When that message travels through the Kafka pipeline and reaches the backend worker servers, the servers are responsible for taking the message out of the queue and writing it into the permanent database, which we'll establish as Cassandra shortly. Those workers use a very specific instruction. They attempt to insert the message into the database using an if-not-exist condition, and they key that condition entirely on the client messaging.
Okay, walk me through the mechanics of that. If the network hiccups and Kafka accidentally sends the same message through the worker servers 3 times in a row, what physically happens at the database level?
All right, so the pub copy arrives. The database looks at the UID, checks its records, sees that this UID does not exist, and writes the message to the disk. 3 milliseconds later, the second copy arrives. The database looks at the UID, checks its records, sees that it already has a row with that exact fingerprint, and it simply drops the request.
It just ignores it.
Exactly. It silently kills the duplicate operation at the storage layer. The third copy arrives, same result.
So the application layer, the servers running the actual chat logic, don't even have to write complex code to check for duplicates. They just blindly try to shove everything into the database, and the database acts as an impermeable filter.
Correct. It's a brilliant application of idempotency. An operation is idempotent if doing it once has the exact same result as doing it 10,000 times. By enforcing this at the database level using the client's UEID, the backend becomes incredibly resilient to network retries.
But the source notes highlight a massive pitfall right here in the data flow, a true senior-level trap that interviewers love to spring on candidates.
For the partitioning trap.
Yes. It has to do with how you organize or partition these billions of messages inside the Kafka queues before they even reach the database. The notes are very explicit. A senior engineer knows to partition Kafka by conversationid and absolutely never by userid.
Let's pause here because I want to challenge this.
Go for it.
As a user, I am the one generating the data. My account is the source. Why wouldn't the system organize the incoming data queues by my specific user? That feels entirely intuitive. It does feel intuitive, and that instinct is exactly why mid-level candidates fail this portion of the system design interview. To understand why partitioning by userid is an architectural disaster, we really need to look at what a Kafka partition physically does.
Okay.
A partition in Kafka is essentially a single, strict, single-file lane of traffic. Messages that are placed into the same partition are absolutely guaranteed to be processed in the exact chronological order they arrived.
Okay, so a partition is a rigid sequential conveyor belt.
Right. However, messages placed in different partitions are processed in parallel by different servers, with zero guarantees regarding which one gets processed first.
Ah, I see where this is going.
Yeah, imagine a highly active user. Let's say you are actively participating in 5 different fast-moving group chats simultaneously. You're firing off messages to a work group, a family group, and a gaming group all at the same time. If the architecture partitions Kafka by your userid, every single message you send, and did it for 5 completely different audiences, is forced onto the exact same single-file conveyor belt.
I'm starting to see the friction here. Why is forcing them onto one belt a problem, though?
Because the people in your family group chat do not care about the message you just sent to your work group chat. But because they are stuck in the same sequential queue, the system has to finish processing your work message before it is allowed to process your family message. You have created an artificial, unnecessary bottleneck. You are mixing the chronological sequence of 5 completely independent conversations.
Oh, wow. And it gets infinitely worse when you consider the other side, right? What about the other 50 people in the work group chat?
Exactly. Their messages are being forced into their own individual userid partitions. So now the backend worker server tasked with assembling the workgroup chat has to somehow monitor 50 different conveyor belts simultaneously, pull messages off them at varying speeds, and try to stitch them back together into a coherent, chronologically accurate timeline for the group chat interface.
That sounds like a synchronization nightmare. Trying to constantly compare timestamps across 50 different physical server nodes just to figure out who actually spoke first. I mean, the locking and sorting required would be horrendous.
It would completely obliterate your 500 millisecond latency budget. The CPU overhead of that synchronization is just astronomical. And that is why the senior call-out is non-negotiable. You must partition the Kafka queue by conversationid.
Okay, let's visualize how that changes the physics of the system. If we partition by conversationid, it means every single message intended for, say, workgroup A, regardless of who sent it across the globe, is mathematically routed onto the exact same Kafka conveyor belt.
Precisely. And because they are all on the same belt, Kafka's physical architecture naturally enforces a strict chronological ordering for that specific conversation.
Oh, so the backend worker server doesn't have to synchronize anything.
Nothing. It just reads that single lane, one message at a time, and it knows with absolute mathematical certainty the exact order those messages should appear on everyone's screen. The ordering is solved at the queue level before the application even touches it.
And it solves the scaling problem beautifully. Because there are millions of different active conversations happening at any given second, Kafka can take those millions of independent conversationid lanes and spread them evenly across hundreds of different physical servers.
Yeah, no single machine gets overwhelmed. It's a perfect example of designing the data architecture to match the physical reality of the product rather than just relying on default database behaviors.
Right. And system design at this scale is always an exercise in matching the storage mechanism to the access pattern, which transitions us perfectly to the core of the backend, the database layer itself.
Let's get into the databases.
We've routed the message securely, we have guaranteed its chronological order, we have stripped out the network duplicates. Now, where does this message live permanently so I can scroll back and read it 3 years from now? Because looking at the storage layer map in our sources, this is not a monolithic architecture. They don't just dump all the application data into one massive SQL server. No, absolutely not. At a scale of 2 billion users, you have to employ what is called polyglot persistence.
Okay, let's pause on polyglot persistence. That sounds like a great consulting buzzword. But you just mean we aren't putting all our eggs in one database basket, right? We are using different types of database engines specifically tailored for different shapes of data.
Exactly. You don't use a hammer to turn a screw.
If we look at the architecture map, the design utilizes PostgreSQL, which is a very traditional, highly structured relational database for certain things. It uses Postgres for user profiles, your username, your hash password, your phone number, and it uses it for group metadata, so the name of a group chat, the avatar image URL, and the list of user IDs in that group.
But wait, why does a traditional relational database like Postgres survive in a design that is handling 100 billion events a day? I thought relational databases were considered the massive bottleneck in hyperscale systems.
Well, relational databases become a bottleneck when you subject them to extreme write-heavy workloads or ask them to perform massive distributed queries. But the access pattern for a user profile is incredibly simple. When a user logs in, the backend just performs a simple point lookup. Select from users where phone number X.
It's just a tiny read.
Right. It is a tiny amount of structured data, and crucially, it is rarely updated.
Yeah.
People don't change their bio or profile picture 100 times a second. Relational databases like Postgres are exceptionally good at maintaining strict data consistency for low-velocity, highly structured data. You can easily shard a Postgres cluster to handle 2 billion user profiles because the queries are just so simple and localized.
Okay, so Postgres handles the slow-moving, structured reference data, but the actual chat history, the 100 billion messages flowing through the system every single day, that data does not go anywhere near PostgreSQL.
No.
The architecture strictly mandates Apache Cassandra. Now, I want to really dig into this because this is a classic system design debate. Why does a NoSQL database like Cassandra utterly conquer a relational database when it comes to storing chat history? Let me throw an analogy at you and let's see if we can break down the mechanics.
Well, I'm ready. Let's hear it.
I picture a relational database like Postgres as an incredibly complex, beautifully cross-referenced library catalog system. Like, it is designed so you can ask it highly complex questions. I can ask Postgres, show me a list of all users who joined the platform in 2023 who live in New York and who have sent more than 5 messages containing the word pizza in the last week.
A very specific query, but yes.
Right. And to answer that, the database has to scan multiple different tables, mathematically match them up, which I know is called a join, and calculate the final result. It is incredibly powerful, but it requires a lot of cognitive overhead, a lot of CPU power from the server.
That is a very accurate description. Relational databases prioritize flexibility and the ability to query data across multiple dimensions using things like B-tree indexes.
Let's unpack a B-tree index because that's the underlying mechanism here, right?
Mm-hmm.
If I understand it correctly, a B-tree is literally a tree structure mapped onto the hard drive. To find a piece of data, the database has to traverse down the branches of the tree.
Right.
But more importantly, when you write new data, the database has to find the exact right leaf on that tree to put the data in. And if that leaf is full, it has to split the leaf, reorganize the tree, and update all the pointers. That involves jumping around the hard drive, doesn't it?
Exactly. It's called random I/O.
Yeah.
The hard drive's read-write head is physically jumping to different locations to update the index. And random I/O is the mortal enemy of high throughput.
Because it's slow.
Yes.
Yeah.
When you're writing 100 billion messages a day, if your database has to jump around reorganizing B-trees for every single message, the disk latency will literally choke the system to death.
Right. And here is the crux of the analogy. A chat application does not ask complicated, multidimensional questions.
Nope.
It doesn't need to join tables to find out who likes pizza. A chat application really only ever asks one extremely specific question over and over and over again. When I open a chat on my phone, the app basically just yells at the database, give me the last 50 messages from conversation ID 12345.
That is the entire access pattern.
So in my analogy, Cassandra is less like a complex library catalog and much more like a massive industrial warehouse filled with filing cabinets. Every single drawer is boldly labeled with a conversation ID. When I open the app, the system just walks directly to that specific drawer, pulls it open, and the newest messages are right there, physically sitting at the very front of the folder. No thinking required. No tree traversal.
That analogy is phenomenally accurate. I
Yeah.
really like that. And the physical reality of how Cassandra implements that filing cabinet is exactly what makes it the undefeated champion for time series data like chat history.
So how does it actually do it?
Well, to understand how it avoids the B-tree problem, we have to look at the specific Cassandra schema highlighted in the source notes. In Cassandra, you define a primary key, but it is split into 2 distinct parts. The partition key, which is set to the conversation ID, and the clustering key, which is set to the message ID, sorted in descending order.
Let's break down the physical mechanics of those two keys. What exactly does the partition key do when the system tries to find my data?
Okay, so Cassandra operates as a massive distributed ring of independent servers. When a query comes in for a specific conversation, Cassandra takes that ID, runs it through a cryptographic hashing algorithm, and the resulting hash tells it exactly which specific physical server in the cluster holds the data for that conversation.
Oh, so that's the label on the filing cabinet drawer.
Precisely. The system doesn't have to broadcast a search across the entire cluster. It calculates the hash and goes straight to the exact machine holding the data. It's an O1 routing operation. Instantaneous.
Okay, so we found the correct server instantly. Now what about the clustering key, which is set to message DESC?
The clustering key dictates how the data is physically laid out on the actual hard drive inside that specific server. Because we instructed it to sort descending by message, and because these IDs are UUIDs or snowflakes, they generally correspond to chronological time. The newest messages are literally the very first bytes of data written sequentially in that block on the disk.
Wow. So they're right at the front.
Right at the front. So when your phone queries where conversation at Keel Valley 50, Cassandra requires 0 joins. It requires 0 B-tree traversal. It goes to the correct server, finds the partition, reads the very first 50 entries straight off the disk sequentially, and returns them. It is a perfectly optimized operation tailored exactly to the UI's requirement.
That is stunningly efficient. It is essentially pre-computing the answer to the query at right time. But wait, if it writes the data sorted sequentially, how does it handle the massive write volume? Doesn't sorting take time? Like, it still has to organize it.
And this is where Cassandra's architecture completely diverges from Postgres. Cassandra uses a log-structured merge tree, or LSM tree, under the hood.
An LSM tree.
Yeah. When a new message arrives, Cassandra does not go looking for a place on the hard drive to insert it. It simply writes the message into an in-memory structure called a mem table. Writing to RAM is instantaneous. Once that mem table gets full, Cassandra takes the entire sorted chunk of data and just flushes it to the hard drive in one massive sequential write.
And we already established that sequential disk writes are incredibly fast.
Exactly. It's just appending data to the end of a file. There is no random I/O. There are no page splits. Cassandra just absorbs the writes in memory and flushes them to disk as fast as the hardware allows. This means you can scale Cassandra horizontally almost infinitely.
So if you get more users, you just add more boxes.
Right. If 100 billion messages a day becomes 200 billion messages a day, you don't need a bigger, more expensive server. You just add more commodity servers to the Cassandra ring. The hashing algorithm automatically redistributes the partitions, and the write throughput scales linearly.
Okay, so we have built an impenetrable pipeline. We have perfect chronological ordering. We have a storage engine that uses sequential disk I/O to basically eat 100 billion messages for breakfast. Storing a one-on-one text message between you and me seems completely solved.
It is.
But this is exactly where the interviewer in our scenario is going to smile, lean forward, and try to break your architecture. Because what happens when we take this elegant, perfectly optimized system and we subject it to a group chat with 100,000 active participants?
Yeah, and that plunges us into the realm of surviving high concurrency, because every single mathematical rule and efficiency we just established begins to aggressively fracture when you multiply the participant count by 100,000.
Let's look at one of the most fundamental UX features of a messaging app, read receipts, the little blue check marks.
Oh, boy.
Right. In a one-on-one chat, the flow is trivial. I send a message, your phone downloads it, your phone sends a tiny network packet back to the server saying I read it, and the server pushes a notification to my phone, turning the checkmark blue. One message sent, one read receipt processed. But what happens if I drop a message into a massive community group?
Let's do the math on the network traffic. If you broadcast a message to a group with 5,000 members, and the group is highly active, you might have 3,000 people open their phones to read it within the first 10 seconds.
That's a lot of read receipts.
That is 3,000 individual read receipt network requests firing back at the backend server almost simultaneously for one single message. Now multiply that by the thousands of messages being sent in that group every day.
So the database would be utterly crushed. If we are trying to update a relational database, say update message read, set read status true, where message X and D user it, user Ds, why doing that 3,000 times a second for a single message would cause massive row locking contention. The database would just grind to a halt.
It is computationally ruinous to track precise, per user read states at that scale. So the interviewer asks you, how do you solve this impossible database bottleneck?
What is the senior call out? How do you optimize the query?
You don't optimize the query, you cheat.
You cheat.
Yes. You fundamentally compromise on the product feature to protect the infrastructure. A senior candidate understands that strict product requirements must often bend to physical engineering realities. Our architectural sources explicitly highlight how platforms like WhatsApp handle this exact dilemma.
Okay.
If you are in a small group chat, maybe 5 or 10 people, WhatsApp will gladly show you the precise list of exactly who has read your message. It tracks the individual receipts because the database load is negligible. But the moment that group size crosses a specific threshold, usually around 20 or 30 people, WhatsApp silently alters the application's behavior. It completely abandons individual tracking and simply displays an aggregate count, read by 47.
I've actually noticed that in the app, I always assumed it was just a UI cleanup to save space and never realized it was a defensive mechanism to protect the database from locking up.
Absolutely. Tracking a single integer counter in a database, just incrementing a number from 46 to 47, is exponentially cheaper than tracking a rapidly expanding list of individual user IDs and their associated timestamps. But even an integer counter has its breaking point.
Wait, really?
Oh yeah. Our notes reference platforms like Discord or Telegram, which host broadcast channels with hundreds of thousands of members. At 200,000 members, even incrementing a single integer counter in a database for every single read event becomes a dangerous write bottleneck.
Because even if it's just one row, you still have 200,000 different threads trying to lock that exact same row to add one to it at the same time.
Exactly.
So what does a system like Discord do? Do they just stop showing view counts entirely?
No, they utilize a fascinating, highly advanced computer science concept called hyperlog.
Hyperlog.
It is a probabilistic data structure. Instead of maintaining a perfect, mathematically exact count of how many unique users have viewed the message, hyperlog uses an algorithm to estimate the cardinality, meaning the number of unique items, with remarkable accuracy, while consuming an incredibly tiny fixed amount of memory. We're talking about a fraction of a kilobyte, regardless of whether it's counting 10 people or 10 million people.
Wait, I really need to understand how that works. How can an algorithm know how many unique people looked at something without actually keeping a list of them or counting them one by one?
It relies on hashing and the statistical probability of binary numbers. Let me give you a conceptual analogy.
Please do.
Imagine you were in a room, and you want to guess how many people are in the room, but you aren't allowed to count them. Instead, you ask everyone to flip a coin until they get heads, and then yell out how many times they had to flip. If the highest number anyone yells out is 3, you can guess there are probably only a few people in the room. But if someone yells out, I had to flip 15 times before I got heads, probability dictates that there must be a massive number of people in the room for someone to have hit that statistically rare streak.
Oh, that's brilliant. So instead of flipping coins, hyperlog takes every user's ID, runs it through a hash function to turn it into a long binary number, and looks for sequences of consecutive zeros.
Exactly. It looks at the maximum number of leading zeros in the hashed user IDs it receives. Finding a hash with a huge string of leading zeros is statistically rare. If it sees one, it knows the overall pool of unique users it is looking at must be very large. It aggregates these probabilities across multiple different buckets to average out the outliers.
Wow.
The result is that when you look at a massive broadcast channel and it says 45,201 views, that number might not be exactly 45,201. The true number might be 45,180 or 45,230.
So the system willingly accepts a tiny margin of error, maybe 1 or 2% in the user interface, to completely eliminate a catastrophic database write bottleneck on the back end.
Exactly.
That is the definition of an acceptable engineering compromise. Now, let's look at another feature that causes a massive computational explosion in group chats: end-to-end encryption, or E2EE.
Yes, because cryptography is incredibly computationally expensive, particularly for the battery and CPU of a mobile device.
Right, so let's walk through the mechanics of the Signal protocol, which WhatsApp and many others use. In a one-on-one chat, it relies on asymmetric encryption. When I send you a message, my phone mathematically locks the message using your specific public key.
Right.
And the backend server cannot read it. It doesn't have the key. The server just acts as a courier, storing the locked box, the ciphertext, and handing it to your phone where your private key unlocks it.
That is beautiful and secure for 2 people.
But if I'm in a group chat with 500 people, does my physical iPhone have to encrypt that exact same text message 500 separate times, generating 500 unique ciphertexts, one for every single person's public key? Because if it does, my phone's battery is going to drop 5% every time I send a meme.
In a naive implementation, yes, that is exactly what would happen. It would be an ON operation,
OFN.
meaning the computational workload increases linearly in direct proportion to the number of members in the group. And yes, your phone's processor would max out, the UI would freeze while it crunches the math, and the battery would drain rapidly. This is another massive senior call-out in the architectural interview. A senior candidate does not let the system default ON encryption. They introduce the cryptographic concept of sender keys.
Okay, if encrypting it 500 times kills the battery, the only logical workaround is that the phone must encrypt the message exactly once. But how can 500 different people with 500 different private keys open the exact same locked box?
They don't use their personal keys to open the box. Instead, the architecture switches from asymmetric encryption to symmetric encryption for the group payload. When you are added to the group, or when you initiate a message, your phone generates a single, highly secure, random session key specific only to that group chat.
Okay.
This session key is then securely distributed to the other 500 members using their individual public keys. This distribution happens quietly in the background.
So everyone in the room now silently holds a copy of the same master key for this specific conversation.
Exactly. Now, when you want to send that meme, your phone encrypts the image payload exactly once using that shared group session key. It is an O1 constant time operation. It takes milliseconds regardless of group size. The server receives that single encrypted payload and efficiently fans it out to all 500 members. Because their devices already possess the shared session key, they can decrypt the payload instantly.
It's an elegant mathematical sidestep. But I immediately see the vulnerability there. What happens if someone leaves the group or gets kicked out? They still have that shared master key sitting on their phone. Could they intercept future network traffic and read the group's messages even after they are gone?
And that is the exact trade-off of symmetric session keys. Key management becomes highly complex. To maintain perfect forward secrecy, the architecture requires key rotation.
Meaning a new key.
Right. The exact moment a member is removed from the group, the sender's application is notified. The application automatically discards the old session key, generates a brand new session key, and securely distributes the new key only to the remaining 499 members. So any message sent after the eviction is encrypted with a key the booted member does not possess.
That makes sense.
But for the vast majority of normal chat operations, sender keys save the mobile client CPU from just grinding to a halt.
It all comes down to mitigating these ON mathematical explosions. Which brings me to the third element of group chat chaos. Presence. The little green dot next to an avatar that tells you someone is currently online. If a platform has 2 billion registered users and 500 million of them are online at any given moment, the backend cannot possibly be broadcasting my specific online status to 2 billion people every time I unlock my phone.
Absolutely not. That is referred to in system design as the presence fan-out problem. If the server attempted to push every single present state change to every single node in the network, the WebSocket gateways would just drown in useless status traffic. The network would collapse. The senior architectural approach to this is a concept called lazy fan-out.
Lazy fan-out. I love the terminology. How lazy you're talking. What does the server actually do?
Yeah. It operates on an extreme need-to-know basis. First of all, the system only ever considers broadcasting your presence to users who are mutually in your contact list. But even that is far too much data. I might have 800 contacts on my phone. I do not need real-time, millisecond-accurate updates on the online status of 800 people simultaneously.
No, of course not.
So the backend optimizes the flow. It only broadcasts your real-time presence to contacts who are currently online and actively have your specific chat window open on their screen at that exact moment.
Wait. So when I open my main inbox view and I see a list of 50 conversations and 10 of them have little green dots, that is an illusion. The server isn't actually pushing that data to me in real time.
It is a highly optimized illusion, yes. If you are merely scrolling through your main inbox, the client application is likely relying on stale, cached data, or perhaps it periodically pulls the server every few minutes for a bulk update. It's only when you physically tap into our specific one-on-one conversation that your application sends a subscription request over the WebSocket. The server essentially registers that event and says, they're actively looking at each other's screens right now. I will open the fire hose and start sending the real-time typing indicators and millisecond accurate online status. The precise moment you hit the back button and close the chat, the server immediately tears down that subscription and stops sending you those updates.
This entire section is just giving me a profound new appreciation for the psychological illusion of the user interface. When I look at a massive, bustling group chat or scroll through a vibrant contact list, the system is actively taking massive shortcuts. It is hiding data, faking real-time updates, and mathematically estimating numbers just to survive my interaction with it. It is incredible.
It really is. And this underlying philosophy that the system must aggressively protect itself from the demands of its own users transitions perfectly into how the architecture handles its dependencies.
Oh.
Because it is one thing to protect yourself from your users. It is another thing entirely to protect yourself from massive external systems that you have absolutely no control over.
Which leads us to decoupling and system reliability. Building blast walls around the core infrastructure. We've spent this whole time discussing the happy path, where both users are online, the network is fast, and the WebSockets are humming. But what happens when the real world intervenes? What happens when I am completely offline, my phone is powered down, and you send me a message?
Okay, so when you are offline, the incoming message hits the backend. And as we establish, it is permanently written into the Cassandra history by conversationit. But simultaneously, the architecture places a pointer to that message into a very specific temporary data structure, the offline message queue.
Queue offline queue.
Yeah. This queue is often implemented in Redis or a separate Cassandra key space, and crucially, it is partitioned entirely by the recipient userid.
Okay, so unlike the permanent history, which is organized by the conversation, this temporary holding cell is just a bucket with my specific name on it.
Yeah.
Everything I missed across all my different group chats and private messages gets dumped into this one bucket.
Correct. And then the backend simply waits. It does not waste CPU cycles continually trying to ping your dead phone. It waits for the client to initiate the action. The moment you turn your phone back on and establish a new WebSocket connection, the very first thing your application does is send a tiny synchronization packet to the server. It contains your last received it.
Right, it's a cursor.
Exactly. Your phone is basically saying, "Hello, I am back online. The very last message I successfully processed was ID 500.
And the backend looks at my specific offline bucket, sees that it contains messages 501 through 550, and it just drains the entire bucket down the WebSocket in one massive payload.
Yes. It drains the queue, delivers the payload to your device, and then deletes the queue to save space. It's a highly efficient, pull-based synchronization. But there's a massive caveat here.
What's that?
While you are offline, there is one more critical action the sender expects the system to take. They want you to know they messaged you. They expect your phone to vibrate in your pocket. They want a push notification.
Ah, yes, the push notification, the absolute bane of backend developers everywhere.
And here is the most critical senior call-out regarding system reliability in this entire architectural deep dive. If you remember nothing else from this discussion, let it be this strict rule. You must never send push notifications synchronously in the main message delivery path.
Okay, I'm going to play the junior developer here and push back on that. Why not? If I send you an urgent message, the whole point is that I want your phone to buzz immediately. Why shouldn't the backend worker server just reach out to Apple or Google, trigger the notification, and then finish processing the message? Why introduce all this complexity?
Because the moment you make a synchronous HTTP request to Apple's push notification service, APNs, or Google's Firebase Cloud Messaging, FCM, you are directly tying the reliability and speed of your entire core messaging engine to the reliability of a third-party server that you do not own and cannot fix.
Let's walk through the physical reality of what happens when that goes wrong. Let's say I'm running the backend worker servers. I have a finite pool of worker threads. Let's say 200 threads per server.
Exactly, a thread pool. If the network is healthy, your server processes a message, writes it to Cassandra, sends the request to Apple, Apple responds in 20 milliseconds, and the thread is freed up to handle the next message. The throughput is massive.
Sounds great.
But what happens if it is Christmas morning? 1 billion people are waking up and activating new iPhones simultaneously. Apple's APN servers are under catastrophic global load and they begin to degrade. Instead of taking 20 milliseconds to respond to your push request, Apple's servers start taking 2,000 milliseconds, 2 full seconds to respond.
Okay, so the push notification takes 2 seconds to arrive. That's not the end of the world.
It is the end of the world for your backend because your core worker thread is blocked. It is sitting there holding an open TCP connection, waiting synchronously for Apple to reply. It cannot process any other chat messages while it waits. Now multiply that. Within a fraction of a second, all 200 threads on your server are stuck waiting on Apple. Your server's CPU usage might be near zero, but it cannot accept any new work.
Oh, I see the cascade. The load balancer sees that my server is healthy but unresponsive, so it routes new chat messages to the next server. Within seconds, that server's 200 threads get stuck waiting on Apple.
Yes. The thread pool exhaustion cascades across your entire global fleet. Memory fills up with incoming messages that have nowhere to go. The load balancers start throwing 502 bad gateway errors. Your application crashes. Because Apple had a slow hour on Christmas morning, WhatsApp goes completely offline for 2 billion people, even for users who have the app open and don't even need a push notification.
That is a catastrophic architectural failure, just because we wanted a phone in a pocket to vibrate. So how does the senior architect solve this? How do you decouple the systems?
We bring Kafka back into the picture to act as a shock absorber.
Okay.
When the core backend worker server processes a message and identifies that the recipient is offline, it does not contact Apple. It simply writes a tiny JSON event payload like user X needs a notification for message Y to a dedicated Kafka topic called notification events. Writing to Kafka takes a fraction of a millisecond. The worker thread then immediately drops the task and moves on to processing the next chat message.
So the core messaging pipeline remains incredibly fast, completely isolated from the latency of the outside world. But then who actually talks to Apple?
You build a completely separate, isolated fleet of microservices. Let's call them the push fleet. This fleet's only job is to sit there and read events off that Kafka notification topic. They grab the events, and they are the ones who make the risky HTTP requests to Apple and Google. If Apple is responding slowly, the threads on the push fleet will absolutely get blocked. The Kafka queue will start to back up. Push notifications might be delayed by 10 minutes. But, and this is the genius of decoupling the core messaging application, the servers handling active text chats for the 500 million people who are currently online are completely unaffected. Your internal delivery metrics remain under 500 milliseconds, regardless of external provider outages.
You essentially build a bulkhead in the ship. The push notification compartment can completely flood with water, but the core messaging engine keeps the ship afloat. That is brilliant.
It is fundamental for survival at hyperscale. But, we spent an hour talking about how the backend protects itself from flaky networks, from external dependencies like Apple, from the immense volume of data. But sometimes, the most dangerous threat to the backend infrastructure is actually the application running right on the user's phone.
Which perfectly sets up our final area of analysis: front-end illusions that save the backend. Because if a front-end client application isn't coded with extreme discipline, it will accidentally launch a distributed denial of service attack against its own servers.
Absolutely. The front end can crush the infrastructure we just spent all this time designing.
Let's start with the most obvious hardware limitation, which is the physical screen and the browser's memory. We talked about chat histories being permanently stored in Cassandra. What happens when a user opens a legacy group chat that has 50,000 messages in it, and they just furiously swipe upward, scrolling as fast as they can, trying to find a link from 3 years ago?
Well, let's look at the mechanics of the DOM, the document object model. Whether it's a web app or a React Native app, rendering a message bubble on the screen requires the device to allocate memory for that specific element. If you try to natively render 50,000 individual message bubbles simultaneously, you're creating 50,000 DOM nodes. The browser's layout engine has to calculate the CSS, the padding, and the margins for every single one of them. The memory allocation spikes to gigabytes. Mobile Safari or Chrome will simply terminate the process to save the phone's RAM. The app crashes.
Exactly. Our source notes indicate that natively rendering 50K complex DOM nodes consumes roughly 2 GB of memory and reduces the scroll frame rate to an unusable 5 frames per second. So the front-end architecture has to utilize a technique called virtual lists, often implemented with libraries like React Window.
Yes.
How does the virtual list illusion actually work under the hood?
It is a profound optimization of memory management. The application might hold the raw data for 50,000 messages in a simple JavaScript array, which takes up almost no memory. But the virtual list component mathematically calculates the user's exact scroll position in pixels. It determines that based on the height of the screen, only messages at array index 400 through 415 should be physically visible right now.
Yeah.
So it only creates the DOM nodes for those 15 messages, plus maybe 3 above and 3 below as a buffer.
Oh, so as I scroll furiously up the screen, the app isn't actually moving 50,000 elements up. It's just taking the DOM nodes that scrolled off the bottom of my screen, teleporting them instant to the top of the screen, and swapping out the text payload inside them with the older data from the array.
Precisely. It recycles a static pool of about 30 DOM nodes over and over again. This keeps the memory footprint absolutely flat, around 50 megabytes, and guarantees a silky smooth 60 frames per second, no matter if you scroll back 5 days or 5 years.
That's amazing.
But fetching historical data introduces a very specific, incredibly annoying UI bug that senior front-end engineers have to solve.
Walk me through the bug. What happens when I hit the top of the buffer?
Imagine you scroll up and hit the oldest message currently loaded in memory. The app detects this, fires an API request to the backend. It says, give me the next 100 older messages. A few milliseconds later, those 100 messages arrive. The front end now has to inject those new elements into the DOM above the message you are currently staring at.
I know exactly what happens next. The physics of a web browser dictate that if you insert height into the top of a container, it violently pushes everything else down. So if I am reading a specific text message and the historical data loads in above it, the text I'm reading will suddenly jump entirely off the bottom of the screen and I lose my place. It is incredibly jarring.
Exactly. To fix this, a senior candidate implements strict scroll position preservation. The modern browser-native way to attempt this is using the CSS scroll anchoring API, specifically setting the rule overflowAnchor.auto. This tells the browser's layout engine to identify the node currently on the screen and automatically adjust the scroll bar to keep that node pinned in place, even if massive amounts of content are inserted above it.
But looking at the source notes, there is a very specific senior callout regarding that CSS trick. They don't trust it.
Right. The callout is that native CSS scroll anchoring is a great baseline, but it notoriously fails in complex edge cases, particularly inside mobile web views, the embedded browsers inside native applications.
Why does it fail?
If an image within the new historical data loads a split second later and changes the height of a container, the CSS anchor will break and the user will still experience that jarring scroll jump. So for production-grade reliability, the architecture dictates manual scroll top delta adjustments.
Let's break down the math on that. How do you manually freeze the screen?
It requires precise timing synchronized with the browser's paint cycle. Just before you inject the 100 new historical messages into the DOM, you execute a JavaScript function to record the exact physical pixel height of the scroll container. Let's say it's 2,000 pixels. Then you inject the messages. This obviously makes the container taller. Immediately, before the browser is allowed to draw the next frame to the user's screen, you measure the new height of the container. Let's say it's now 3,500 pixels.
Okay.
You calculate the difference of the delta, which is 1,500 pixels. Finally, you manually add that exact delta to the user's current scroll position value.
So the container grew by 1,500 pixels, and you instantly forced the scroll bar down by 1,500 pixels. Because you did it before the next frame painted, the physical pixels the user's looking at never actually moved on the glass.
Precisely. It is completely seamless.
Yeah.
It is those microscopic, mathematically intense adjustments that make an application feel premium and solid rather than janky and fragile. But virtual list and scroll math just save the client's memory. How does the front-end code actively save the back-end servers from being overwhelmed?
That's a great question.
Through aggressive, mathematically enforced throttling and debouncing, governed by what architects call an event frequency budget. We touched on the danger of read receipts earlier. If a user is using a virtual list to scroll rapidly through 500 unread messages in a channel, we absolutely cannot allow the front end to fire a distinct network request to the back end for every single message ID that flashes across the viewport.
Right. 500 network requests from one user scrolling for 2 seconds is a self-inflicted DDoS attack. The back-end load balancers would be screaming.
Exactly. So the front end utilizes an intersection observer. This is a highly efficient browser API that detects exactly when an element enters the visible viewport.
I've heard of that.
As you scroll, the intersection observer quietly builds an array of all the message IDs you have visually consumed. It holds onto that list in local memory. It waits. And then, enforced by a script timer only once every 500 milliseconds, it takes that entire batch of collected IDs and transmits them to the server in one single compressed network request. You reduce 500 potential TCP connections down to a single highly efficient payload.
That is so smart. What about typing indicators? The little John is typing bubbles. Those seem incredibly noisy from a network perspective.
Typing indicators are fascinating because they're essentially useless data that we process purely for psychological comfort. When you start typing a paragraph, your phone does not send a WebSocket message to the server for every single keystroke. That would be absurd. Instead, the application debounces the event.
Walk me through a debounce mechanism in this context.
Debouncing means delaying the execution of a function until a certain amount of quiet time has passed. As you type, the app resets a timer. It waits for you to pause your fingers for roughly 300 milliseconds. The moment it detects that pause, it concludes you're actively engaged, and it sends a single user as typing state change to the backend.
And the backend stores that temporary state in Redis and pushes it to my screen. But what happens if the sender's phone completely dies mid-sentence? I've seen situations on older, less sophisticated chat apps where it says a user is typing for 3 hours straight.
Oh yeah, the dreaded infinite typing bug. That occurs when an architecture relies on the client application to send an explicit user-stopped typing event.
Right.
If the app crashes or the phone's battery dies, that stop event is never transmitted over the network. The backend server remains completely unaware, and it continues broadcasting the typing status forever. A senior architectural design completely eliminates this vulnerability by enforcing a time to live, or TTL, on the server side.
How does the server-side TTL fix a client-side failure?
When the backend receives the isTyping event, it stores that flag in the Redis in-memory cache, but it attaches a strict 3-second expiration timer to the key. Every time you type a few more characters and your client sends a new debounce event, the server resets that 3-second timer back to full.
Okay, I see.
But if your phone suddenly dies and goes silent, the server doesn't panic. The 3-second timer simply runs out, and Redis's internal garbage collection automatically deletes the key. The typing indicator clears itself across the network. The system is fundamentally designed to gracefully recover from client failure without requiring explicit stop commands.
That is incredibly elegant. You design the backend so that silence naturally heals the state. Okay, we have time for one final front-end illusion, and this is perhaps the most deceptive one in modern UX media uploads.
Oh, this is a fun one.
When I send a massive 4K video to a friend on iMessage or WhatsApp, the message bubble appears in my chat timeline instantly. It has a blurry thumbnail, I can see the layout, and I can immediately lock my phone and put it in my pocket. It feels instantaneous. But I know for an absolute fact that transmitting a 500 megabyte video file over a cellular network takes significant time. What is the specific trick happening here?
This is the absolute pinnacle of what we call optimistic UI. Let's look at how a junior engineer would build this. A junior developer builds a sequential form. You select the 500 megabyte video, you hit send, the user interface locks up and shows a loading spinner, and you are forced to stare at that spinner while the entire file uploads over TCP to the server. Then and only then does the server acknowledge receipt and the message bubble finally renders on your screen. It is a terrible, highly frustrating user experience that exposes the physical latency of the network.
I've used apps that do that. You just sit there praying the signal doesn't drop.
Bro.
So how does the senior candidate architect the optimistic approach?
A senior design strictly mandates that you never, ever block the user's flow. The exact millisecond you hit send on that 4K video, the front-end client executes a series of tasks instantaneously. First, it analyzes the very first frame of the local video file. It generates a tiny, low-resolution thumbnail, or even faster, a mathematical string representation of the colors called a blur hash. This takes milliseconds of CPU time. Then, it immediately renders the complete message bubble into your chat history DOM using that local thumbnail. It writes a record to your phone's local SQLite database, marking the message status as sending.
So the user interface is literally lying to me. It is projecting a future state, showing me the message in the timeline as if the network transaction has already completed.
Exactly. That is the optimistic part. It assumes ultimate success in order to maintain the psychological illusion of instantaneous speed. Meanwhile, completely hidden in the background, a background worker process takes that massive 500 megabyte video file and begins to aggressively chunk it.
Chunk it.
Yeah, it mathematically slices the file into small 5 megabyte pieces.
I want to focus on that chunking. Why go through the computational effort of slicing it up? Why not just stream the whole file via a single PUT request to an Amazon S3 bucket?
Because mobile networks are inherently hostile environments. If you attempt to upload a 500 megabyte file in one continuous TCP stream, and you are driving in a car and enter a tunnel at the 499 megabyte mark, the connection drops.
Right.
The server discards the incomplete file, and when you exit the tunnel, your phone has to start the entire 500 megabyte upload over from scratch. That wastes massive amounts of cellular bandwidth, drains the battery, and infuriates the user. By chunking it into 5 megabyte pieces, you create a highly resilient, resumable upload architecture.
I see the mechanics. If I hit the tunnel, the system simply notes that chunk number 42 failed to transmit.
Precisely. When your phone regains cellular signal, the background worker doesn't start over. It just resumes uploading starting exactly at chunk 42. It saves data, saves battery, and guarantees that the file will eventually reach the server, regardless of network conditions.
And the entire time this complex, resumable upload is fighting the cellular network in the background, the user has absolutely no idea. They just saw the bubble appear instantly and went on with their day.
Right. And once all the chunks successfully land in the cloud storage bucket, and the backend stitches them together and generates the final public URL for the video, the server sends a tiny WebSocket acknowledgement back to your phone. The phone quietly updates its local database status from sending to sent, replacing the local blur hash thumbnail with the official server-backed asset.
Wow.
It is an incredibly complex orchestration of background tasks, chunked multi-part uploads, and local database state management, all designed for one single purpose: to hide the latency of the real world from the user.
And looking back across all of our architectural sources today, from the WebSocket gateways to Cassandra, from Hyperlog to optimistic UI, it perfectly loops back to the overarching theme of this entire discussion.
Yeah.
Building for massive scale handling 2 billion users and 100 billion messages a day is fundamentally not about writing a bigger check to a cloud provider for larger servers.
Exactly. Throwing hardware at a bad architecture just results in a faster, much more expensive crash. Scaling is about intelligent, ruthless decoupling. It is about recognizing that synchronous operations, like holding a thread open while waiting for an Apple push notification, are fatal flaws that will cascade and destroy your system.
It is about choosing the exact right tool tailored to the precise physics of your data access pattern. You don't use Postgres for chat history because a random I/O B-tree traversal is the wrong physical mechanism. You use Cassandra because its sequential LSM tree and partition model perfectly maps to the requirement of a rapid latest N query.
And perhaps most importantly, as we saw with read receipts, it is about knowing exactly when and how to compromise on the product vision for the sake of system survival. A junior engineer tries to track exactly 200,000 individual read receipts and locks up the database. A senior engineer implements a probabilistic hyperlog algorithm, gives the user an approximate count, and keeps the infrastructure humming along smoothly. It is the art of acceptable compromise.
It really is an art form. And the systems we've dissected today, the Kafka pipelines, the Cassandra rings, the virtual DOM lists, these have been honed over the last decade into highly predictable, proven paradigms. But they were all perfected for human-to-human interaction, which leaves us with a final, forward-looking thought to ponder as we wrap up.
The landscape is definitely shifting.
It is. These architectures were built for human thumbs. We type relatively slowly, we read slowly. Even a massive broadcast group chat is ultimately bounded by human attention spans. But look at where the industry is aggressively moving right now. Chat platforms are rapidly evolving into the primary user interface for interacting with continuous, heavy compute, artificial intelligence models.
That's a great point.
We aren't just texting our friends anymore. We are dropping autonomous AI agents into group chats to argue with each other, to research live web topics, and to summarize massive documents on the fly.
And those agents don't type 60 words a minute. The concurrency models are about to be completely inverted.
Exactly. An AI agent might generate thousands of rapid-fire micro-responses, function calls, and state updates per second. So the provocative question for you to mull over today is this. As the volume of automated machine-to-machine chatter within our messaging apps explodes, how will these proven paradigms have to evolve?
Will they even survive?
Right. Will the 500 millisecond delivery expectation even survive when a single user prompt triggers a cascade of 1 million back-end AI events? Will the Kafka and Redis pipeline be enough to absorb the shock, or are architects going to have to design entirely new, fundamentally different storage and routing mechanisms to survive the next generation of automated concurrency? Think about the sheer physics of that the next time you casually send a text.
It is going to be a fascinating and likely highly disruptive architectural evolution to watch unfold.
Thank you for joining us on this deep dive into the architecture of real-time messaging. Until next time.